Hello, everyone. Welcome to Lecture 9 on um, Introductory Statistics. And in today's lecture, we're going to talk about Section 2 in Chapter 4, complements, unions, and intersections. Now, we will introduce these four event operations. So one is a complement, second is a union, third is intersection, and finally is a difference. Well, the difference is a special type of the intersection and also complements. We'll introduce later. Now, firstly, let's talk about the complements. What do we mean by a complement? So let S be the sample space of a random experiment, and let E be any event. Then we say the complement of this event E, denoted by EC or E prime, is what? Is defined to be the set of all the outcomes in the sample space, but not in E. Okay, so it's everything in the sample space, but not in E. Okay, so that is the Venn diagram here. Okay, say this is E. Now that is everything what? Everything not in E. Okay, so that's everything not in E. Okay, so that is what we mean. It is in the sample space, but not in E. Okay, so in logic terms, we say not E. Okay, the not E. All right, so let's consider an example here. Consider this example. We are drawing a card at random from a standard deck of playing cards. The sample space is going to be the set of all the 52 cards. A be the event that a face card is drawn, and B be the event that a red card is drawn. Then we're trying to find the complement of A and the complement of B. Okay, now for this one, here is a table of all the outcomes from of this experiment. Okay, so in a standard deck of playing cards, there are 4 suits: clubs, diamonds, hearts, and spades. Now in each suit, we have these different card values: ace, 2 through 10, and jack, queen, and king. So among these values, jack, queen, and king, these are face values, face cards, jack, queen, and king. And from 2 to 10, these are number cards. These are number cards. And then this is ace. So you see that in each suit, we have what? 1 to 10, 13. We have 13 cards in each suit. So in total, we have what? 13 times 4, that's 52. 52 cards. Okay, so if we randomly select one from this standard deck, then we got, the possible outcome is going to be each one of them, right? So therefore, the sample space is the set of all the 52 cards. That is our sample space. Now, what is A is the event that a face card is drawn. So face card, that is to say, okay, so that is all the outcomes in the event A. Face card, maybe club, jack, club, queen, and club, queen, king, and so on, right? So they are face cards, all the jacks and the queens and kings. So this is our event A. It consists of all the face cards. Event B is the event that a red card is drawn. So for a red card, that means it is a diamond or heart. Okay, in diamond or heart, they are red in a standard deck. Okay, so now, in other words, B is the event what? Okay, it consists of all these diamonds and hearts. Okay, now we want to find the complement of A. So what is A complement. So that is not A. Not A means what? Not a face card. Okay, not a face card. So we can write everything in the sample space in the deck that is not a face card. Not a face card. So that is what? You can have clubs in the clubs at CA through C10, right? So club ace till club 10. Now, and similarly, we have the diamond ace to diamond 10, heart A through heart 10, and what? Finally is spade A to spade 10. Okay, so this is the set of all the outcomes that is not a face card. All right, that is not a face card. So that is the complement of A. So that is consists of the outcomes that is not in the sample space, not in A, but in the sample space. Similarly, we can find a B complement. Now, B complement, B is the event that a red card is drawn. So the complement of B is what? It's going to be not red. Not red, it can be what? Clubs and spades. So we know that is C of A through what? Through all the way to CK, right? C king, club king. So they are all not red. And similarly, we have what? Spade ace till spade king. Okay, so this is going to be what? Not red. So which is the complement of B. Now, all right, so this is the example about the complement of the event, right? So the complement of A, that means not A, right? Not a face card. The B complement, that's not B, not a red card. Okay. Now let's consider this example. Okay, so assume there are 100 people living in a small town. The following two-way contingency table gives a breakdown of the population according to gender and tobacco use. A person is randomly selected. Find the probability of the following events. Okay, now the person A is a person is not a smoker. Okay, as a not a smoker, so smoker that's denoted S. So not a smoker, that's a complement of S. So that is non-smoker, right? So how many out there are non-smokers? So we see that that's what? 26 plus 39. That is what? 65, right? So therefore, the probability for non-smoker equals N of non-smoker over M, where M is 100, the total number, right? 65 over 100, that's 0.65. B is not a male, so that's a male complement, which is female, right? So therefore, N of male complement equals what? Females. So that's 12 plus 39. That is what? 51. Okay, so therefore, the probability for not male equals N of not male over M. That's 51 over 100. That's 0.51. And C. Okay, the person is not a female smoker. So not a female smoker, that is what? Female smoker complement, right? Not female smoker. So how many are there? Female smoker complement. So that is what? That is going to be, there are 12 female smokers. I believe every others, right? There are not female smokers. So here's male smoker, male non-smoker, and female non-smoker, right? So that is the all the other not female smokers. So we see that it's 23 plus 26 plus 39. I think that's 88. Okay, so therefore the probability of not female smoker equals n female smoker complement over m equals what? Equals 88 over 100 equals 0.88. Okay, so that is what we have. Here is A, sorry. All right, so basically, we have this concept of complement. Complement of event means not this event. Okay, so smoker, not a smoker. Male, not a male. Female smoker, not a female smoker. Right? That's a complement. Now the next concept operation is the union. Okay, let A, B be two events. Then the union of A and B denoted by A union B is a set of all the outcomes that are either in A or B or both. Okay, so let's draw the Venn diagram here. Okay, so that this is A and this is B. Okay, now this is a set of all the outcomes that are either in A. Okay, say this is the outcomes that are only in A, right? Or in B, or what? Or both. So that's the intersection part. Okay, so this shaded area, either in A or B or both, this is called the union. Okay, the union of A and B. Okay, so now here is some special case. Okay, so A is union B. All right, union B. Okay, so either in A or B or both. Okay, now let's consider again this example. A is again the face card, B is the red card, then what is A union B? Okay, so again, we know that this is the face card, and this is the red card. Diamonds and hearts are red, right? So then we want to see the union of A and B. Okay, so A union B is what? The set consisting of all the outcomes that are either in A. In this case, A is the face card, so only in A, that's what? CJ, CQ, CK, and only in A. So we're not talking about the overlap part, are just those outcomes in A as SJ, SQ, SK, and these are the outcomes only in A. And then let's talk about those outcomes only in B. Okay, only in B, that's what? D of A till D10. H of A till H of 10. Okay, these are the outcomes that are only in B. Okay, either in A or B or both. Or both, that's what? DJ, DK, DK, Q, K, and what? HJ, HQ, and HK. So these are what? In both A and B. So either in A or B or both. Okay, so that is the union of A and B. Now, this set can also be written in a way that is simpler. Okay, so you have what? CJ, CQ, and CK. And then for the diamonds, as you can see, from diamond A to diamond K, they are all in the union. So we can just write down as what? dA till dk. Okay, and similarly for hearts, it's a hearts A till heart K. And finally what? It is spade, J, spade, queen, and spade, king. So that is the union. That is a union. Okay. All right. So either in A or both, or B, or both. Okay. Now consider this example. We have ruling a Faraday. A is 1, 3. B is the event 3, 4, 5. We want to find the union of A and B. Okay, so A union B equals either in A, so on the element that belongs only to A, so that is 1, or B, so 3 and 5, or both, right? 3 here is both in, no, here is 4 and 5, and this is 3. Okay, so 1, 4, 5, this is only in A, this is only in B, and this is in both. Okay, so now in the future, if you're familiar with this, you can just write down as 1, 3, 4, 5. Okay, so in the future, you don't have to write down in this order. You can simply put it in like this way. Okay, this is the union of A and B. Now, order doesn't matter in a set, and it must be all distinct. Okay, so some of us may write down as what? 1, 3, 3, 4, 5. Now, this will not be right. Okay, this is not good because you have a repeated 3, which is not allowed in a set. Okay, in the set, it must consist of all distinct values. All right, so you cannot write down this way. So this is A union B. Now, another thing is we want to find A union B complement. So in order to find the union of A and B complement, let's firstly find the B complement. So the sample space for a rolling die, that's going to be 1, 2, 3, 4, 5, 4, 5, and 6. Okay, so the B complement is going to be what? Everything that is not in B, that's what? 1, 2, and 6. So this is the complement of B, right? Now from this one, we see A union B complement is simply what? 1, 3, union B complement 1, 2, 6. Now this one is either in A, 3, right? B, 2, 6, and in both, that's 1, right? So that is going to be the union, right? Or you can write it down as 1, 2, 3, 6 if you wish to. All right, so that's how we find the union of two events, okay? Either in A or both, or B or both. Next, we are going to talk about the intersection. All right, that A, B be two events. The intersection of A and B, denoted by this notation, is the set consisting of all the common outcomes in both A and B. Okay, so I'm going to again draw a Venn diagram. Say this is my A, this is my B. Then the common value, okay, the common outcomes, that is the intersection. A intersect B. Okay, A intersect B. So that is the intersection. Now, again, consider this example. A is a face card, B is the red card. So as we know, this is in A, and this red card is in B. Now A intersect B, or be careful, intersection, right, is what? Is the common values in A and B. So that is what? That is here, right? So diamonds, this one. So it's diamond jack, diamond queen, diamond king, had a heart jack, heart queen, and heart king. So they are all face card, and at the same time, they are also red, right? So face, both face and red. Okay, so this is the intersection. So it consists of what? All the common values, common outcomes in A and B. Now consider this example again. Now here a Faraday, A and B are given here. So what is A intersect B? So that is a common value of A and B. So we see that what? 3 is a common value, right? So therefore, the intersection of A and B is simply, the set. Okay, and also B complement, as we can see, this we already found is 1, 2, 6, and then therefore A intersect B complement is 1, 3 intersect B complement is 1, 2, 6. So that is what? Simply 1, right? Simply 1. So the 1 is a common value. Okay, so that is the intersection of A and B complement. The next we are going to talk about is the difference. Well, the difference of B from A, denoted by what? A minus B, is what? The intersection of A and B complement. Okay, so in Venn diagram, I'm going to show you as this. So I'll say this is A, and this is B, and it's a set consisting of all the outcomes of even A that are not outcomes of even B. So in A, but not in B. Okay, so A minus B equals what? A intersect B complement. Okay, so it's not including the intersection part. So basically, we exclude the intersection from A because the intersection also belongs to B. Right, so that is the set of all the outcomes of A that are not outcomes of B. So in other words, it is in A, but not in B. Okay, so in A, but not in B. All right, A intersect B complement. Okay, that is the elements that is only in A, all right, not in B. Similarly, we can also have in B, not in A. Okay, so this part that is only in B, so that's B minus A is what? Is B intersect A complement. Okay, so we say it is in B, but not in A. All right, see, because here is A complement, so it's not in A, and but in B, right? In B, but not in A. Okay, so this is the difference, right, between of A from B from A, or the difference of A from B. Okay, so they are actually an intersection. Okay, they are actually an intersection, right? So, but you need to know what do we mean by A minus B? That is in A, not B, right? B minus A means in B, not A. Now again, let's consider this example. All right, so it's a face card. This is a red card. We want to find A intersect B complement. So this is my A, and this is my B. Okay, so we want to say A intersect B complement. So that is what? It must be in A, but what? Not in B. Not in B. All right, in A, not in B. So as you can see, in A, it must be face cards. Not in B, that's not diamonds or hearts, right? So it must be what? Clubs or spades, and also it must be face card. So club jack, club queen, club king, spade jack, spade queen, spade king. Okay, so that is in A, not in B, right? So what about this one? So see if you can find this. What about A complement intersect B? So that is what? in B, but not in A, right? In B, not in A. So in B, it's a red card, not in A, cannot be face. So it's going to be what? Diamond S to diamond 10, heart S to heart 10. Okay, so that's the difference. In A, not in B. In B, not in A. Okay. Consider this example. Here, A and B here. So what is this intersection? So A complement intersect B. That's what? In B, but not in A. So in B, but not in A. So you see that this is 3 is in A. So you cannot include 3 in this set. So that is going to be what? 4 and 5. Okay. So similarly, what about A intersect B complement? So this is going to be in A, but not in B, right? So in A, not in B. So that is what? That is simply in A here, but not in B. So 3 must be deleted. So it is just this one. Very good. So this is a difference, right? This is a difference. Now let's consider this example. All right, we want to consider the following events in example 4.3. So remember, let's recall this example. It is an example of flipping a coin 3 times. Okay, and the order of heads and tails are recorded. So the sample space is given here. There are 8 possible outcomes. So here is what? Head, 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 tail, and so on. Right, this is the sample space. And A is an event for which the second flip is a tail. Right, the second flip is a tail. So second is tail, second is tail, second is tail, second tail. Excuse me. Now B is the event that you have 2 heads, 1 tail. So you see that 2 heads, 1 tail, 2 heads, 1 tail, 2 heads, 1 tail. And now we want to find what? We want to find the following events. Okay, A is A complement and B complement. So what is A complement? Let's do this one here. A complement is everything in the sample space that is not in A. Not in A. Okay, so not in A, as we can see, right? So is this one in A or not? This is not in A. So not in A is good. So it's in the complement, right? So how about this one? Is this one in A or not? It's not in A, so it's good. So we have H, H, T. Now how about this one? Well, this one is in A, right? And this one is in A, so we do not do that. This one is also in A. This one is not in A, right? So it's in the complement. And this one is not in A, so it's also in the complement. This is in A, this is in A, right? So therefore, these are all the outcomes that are not in A. So therefore, A complement is a set consisting of all these outcomes that are not in A. Similarly, we can find the B complement. It's the set consisting of all the outcomes that is not in B. Okay, so again, let's do that again, right? So is this one in B or not? It's not in B, so H is in the complement of B. How about this one? Oh, this one is, right? So this one is in B. Okay, so it's not in the complement. How about this? This is also in B. Now this is not in B, so it is in the complement. This one is in B. This one is not. Okay, T, H, T, TTH is not, and finally TTT. Okay, so therefore we have B complement is the set consisting of all the outcomes that is not in B. Okay, so this is our A. Now let's consider B. Okay, consider B here. A union B. Okay, now as we know, what is the union? The union is the set consisting of all the outcomes that are either in A or B or both. Okay, so either in A. Now you one thing you want to realize that these are the outcomes that are only in A, right? So we are going to include these three first. So these are only in A, and then those are only in B. So that is this one and this one. And then what? Then in both A and B. So that is going to be H, T, H. Okay. So therefore, we will have this the union either in A or B or both. Right? Either in A or B or both. Now, of course, this what? Intersection, right? So A intersect B is simply the common value between A and B. So as you can see, that is what? This the common value. So I believe that's the only common outcome between A and B. Okay, therefore, this intersection is this. Okay, this is B, and similarly we can see. So A intersect B complement. So A intersect B complement, that is the common values. That is what? That is in A, not in B, right? So in A, not in B. Okay, firstly in A, not in B. So I believe this is just these three, right? So because what? This one must be deleted because this one is also in B. So therefore we have H, T, 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 H, and T, T, T. So this is A intersect B complement in A, not in B. Now similarly, we can find A complement intersect B equals. Okay, so this is what? In B, but not in A. Okay, not in A, in B. So what do we have? So again, you can see that these two are in B, but you have to delete this one because this value is also in A. So therefore, we have what? H, H, T, T, H, H. Okay, so that's how we solve this problem, right? So you have the complements, the union, intersection, the differences. Very good. Okay. Now let's consider a special relationship between two events. Okay, so if all the outcomes in event A are also outcomes in event B, then A is said to be a subset of event B. So denoted by A, it is denoted by this. Okay, so this is raised as A is a subset of B. So in Venn diagram, it looks like this. Okay, say that this is our B. Now A is simply part of A. A is simply part of B. Now sometimes this notation is also using as just this. Just this will also mean A is a subset of B. Okay. Now let's consider an example. Ruling a six-sided regular die, the sample space is given here, 1 through 6. Now A is a 2, 3, 4, B is a 2, 3, 4, 5, C is a 1, 2, 4, 6. Okay. Now since all the outcomes in A are also outcomes in B. So you can see A here, 2, 3, 4 is a part of B, right? 2, 3, 4 are all in B as well. So therefore, A is a subset of B. So we denote A is a subset of B. Now, however, A is not a subset of C. Okay, so A is not a subset of C. Why? Because what? This A consists of 2, 3, 4. C is 1, 2, 4, 6. Now, 3 here is in A, but 3 is not in C, right? So the existence of 3 here that is in A but not in C means what? Not all the outcome in A also outcomes in B. There exists an outcome in A that is not the event in C. Okay, so therefore what? At least one outcome 3 is in A but not in C. Okay, so therefore we say that A is not an event, a subset of C. Okay. Now, since the sample space consists of the set of all outcomes, so every event is a subset of the sample space. Now consider this proposition. Okay, if A is a subset of B, then the union is B, which is a larger set, and the intersection is a smaller one. Okay, so let me just show you in the Venn diagram here. So this is, okay, let me just draw another one here. Say that this is B, this is A. So the union, either in A or B or both, that is going to be everything about B. So that is B. Okay. Well, the intersection is going to be the common values. That's just A. Okay, so A intersect B is simply A. Okay. So that's what we have. All right. So if A is a subset of B, then their union is simply the larger set, which is B. Now their intersection is going to be the smaller one. So that is A. Since, well, for any set, we know that is a subset of S. So we will, the sample space. So therefore what? The union is going to be the sample space, and their intersection is simply the even A. Okay, so that is the property, the corollary. Okay, so we will have this. Okay, all right. I think that's then let's just introduce this concept, and then we will solve at here. Okay, so now the event are mutually exclusive events. The events consist of no outcomes is called a null event. All right, so denoted by this one. It's a null event. There's nothing inside this event. Now, then two events are said to be mutually exclusive or disjoint if their intersection is null. Okay, so in the Venn diagram, we may have what? Disjoint. Okay, so this is A, this is B. So you can see that they have no common values. In other words, the intersection is what? Empty. There's nothing in their common parts. They have no common values. So therefore, in this case, all right, their intersection is the null event. Now we say what? A and B are said to be mutually exclusive. They are disjoint. Okay. They are mutually exclusive if they have no common outcomes. Let's consider this example. Rolling a six-sided regular die, A is the odd number, B is the even number, and A and B are mutually exclusive, right? So you can see that A intersect B, there's nothing in common, right? So therefore, we say that A and B are mutually exclusive. Okay. All right, I will stop here and we will continue in the next lecture. Thank you for your attention. See you next time.